So we're going to do the last page of the notes, page 26, for some titrations, and it has that little chart at the bottom, which you guys don't know, that has never been in the notes, and then it just suddenly shows up in the study set. And as someone kindly commented earlier, they said, yeah, I didn't really know how to do it. I just copied your answers. So if you do that with the study set, do make sure you go back and actually try the problems. So the first thing we want to do is write our equation. And it's because as soon as you see a strong base, you want to, or a strong acid, HCl, we want to write out our equation. So acetic acid, I would give you the formula. But here we go, first bonus of the day. Do any of you who are here know the formula of acetic acid?
I do.
Go for it.
Is it CH3COOH?
It is. I know, you all actually are going, oh, I knew that, because I keep using it as an example. It's because I know the Ka off the top of my head. Here you go, Harrison. Do you know the Ka?
1.8 times 10 to the negative 5?
Yeah. That one shows up, and it's actually, interestingly enough, the Kb of NH3. And they keep showing up only because I know those in my head, and so I don't have to sit there and flip through notes. All right, so this is acetic acid, CH3CO2H or COOH. This is the hydrogen at the end that comes off. And then we're going to react it with NaOH. These are titration reactions. Whenever you add NaOH or HCl also to a buffer, it's a one-way reaction. So it's easier actually than what we started with, because you know you're always moving forward. So the sodium and the hydrogen are going to switch places. And that's acetate. You can put the sodium on because it is with it, but they're in water. The sodium's a spectator ion. That was a question on the first lab about ions that are just swimming around. It's there. It doesn't influence the pH. It doesn't precipitate. It really doesn't do anything. But when we get to the chart at the bottom of the page, it is truly partnered with this part. And so you can ponder that. All right, we're going to do mice. And the M is there because our first step, here we go, so Harrison, you don't get to answer. Does anybody else remember what the M stands for, or what our extra step is?
Finding moles.
It is. That's why it's a mice chart instead of an ice chart. So we're going to find moles. These we have volume times molarity. On the next one, we're going to do it starting with grams to find moles. So the acetic acid, change your volume to liters. Having helped a number of people, I just move my place value, divide by 1,000 on your calculator. Just be careful, because for this one, look at that, I picked easy numbers for myself again. So that should be 0.01 moles. Putting your units. When you do it here with the 90, it's 0.09 liters times its 0.1 molar. All right, so this would be 0.009. We're really close to the equivalence point on this one, but the equivalence point, they would have to be exactly equal. So we're before the equivalence point. We're at the point where you're still gently going down, or I'm sorry, this one's going uphill because it's an acid plus a base. And we're just right before the sharp cliff uphill. So we're going to subtract the smaller number. And it is a lot of busy work on your homework, your lab. I found a major typo on your lab, so I'm fixing it. I knew myself well enough to know there would be one. So the reactants, it was a question somebody asked me earlier. On these problems with titrations and buffers, you do subtract the reactants and you add to the product. Because they're not actually equilibrium, they're one-way reactions. This is 9, sorry. All right. I like to put a little label because, as you notice, sometimes the acid's on the reactant side and sometimes the acid's on the base side. So I like to put a little A so I know that's my acid, and then this would be my conjugate base. All right, so that way when I plug in, I know what I'm doing. I highly recommend that, well, you state your formula, and I have you keep stating this because none of you need to look it up anymore, hopefully, because it becomes so ingrained. And when you get into organic chemistry, you'll be grateful because you guys will all know it, and you'll just be like, oh, this is what it is. All right, the Ka, you could look it up on that chart, or I try to give it to you so we all have the same. We plug in, this is not X squared, we have the conjugate base. So here's the big question that I left it as moles, and I can on this one. So the question is, why can't I? I've asked this at the last two recordings. So if you've listened and tried some of your homework, why you can, if you're ever in doubt, go to molarity, change it, divide by the total volume, which is actually easy here because we know that. But any of you can jump in for that bonus point.
The proportion of moles to the volume is the same for both conjugate base and the acid.
Right, so you'd be dividing by the 0.19 liters for both of them. So the ratio will still be the same, or the proportion. So we'd rearrange and we'd solve for X. I'm not going to go through all the steps, you guys should. X, I recommend you always label X is equal to what? If it is the Ka, it's most likely your hydronium. If it's the Kb, which we will get one of those, then it's your hydroxide, and then you have that extra step. And then you just punch in, get your pH, so 5.70. Now, something I did not talk about, but when you're in that place, I'm going to sketch a titration curve here. Yeah, I drew these yesterday. You start low. It's a weak acid, so your pH is probably going to be 2 to 3, somewhere in that range when you start, and you have this gentle slope. And this is where we are right now on this problem. We're somewhere on this slope. We're actually probably over here. But what's happening on the slope is you have the conjugate, in this case, the conjugate base plus the weak acid are determining your pH, which means you have a buffer. And that's why I wanted you to feel comfortable with buffers. That means that in this range, your pH is going to be around the exponent of the Ka. And our exponent is -5. So somebody asked me, what do you mean around? It's going to be in like a plus or minus 1, plus or minus, because it is going up, like right in the middle, it is exactly. But we are in that range. And then here we would suddenly see an up. And it is straight up because we get to the equivalence point. But we're not going to do that on this one. We can do it on the next one, because we do an equivalence. Questions on our first one? All right. So number 2. First thing, you can read through it. I see we're going to be adding NaOH to the Hochel. A question came up many years ago. A student got really irritated with me. He said, why is it written as HOCl instead of HClO? And they're the same thing. And he wanted to know why. It has to do, I don't know why. Some people write it as HOCl because then you can call it Hochel. And some people write it as HClO. It is that hydrogen that makes it an acid. I like to always write the strong second. It's just a habit I get into, and it doesn't matter which comes first and second. All right, this is the hydrogen that comes off. I think what frustrated the student was when he saw the H and the O together, he kept making him think it was a base. But it is an acid because the NaOH is a base. So this hydrogen is going to come over and combine with the NaOH. It's going to have to switch places with the sodium. So the sodium is now going to be with the OCl. On the midterm, there was like you had to show reactions of acids and bases, and a lot of you combined the hydrogen and you didn't take the sodium off. The hydrogen and sodium would have to switch places, or you can cross the sodium out, but that's where it would be. And we do show the sodium first, unless it's an organic compound, which is carbon-based, and then the sodium is often shown second. That's a lot of information, but it's questions that a lot of people have been asking since way back in 221, and now it should start making some sense why you may see it both ways. On this one, you would not show the sodium after, because this is not organic. All right, this is my weak acid, and this is my conjugate base. You don't need to label them, but I know somebody's probably pondering that. And we're going to do a mice chart because we see a strong NaOH. And again, it will be NaOH if we're adding a strong base. If we're adding a strong acid, I stick with HCl, but it could be any of the strongs. We are not going to do calculations of a weak plus a weak because that requires more math than we're going to work with here. All right, we're going to do our mice chart. This one's similar to the one above, except for one piece, which is it starts you with 0.35 grams. And so to change your grams to moles, periodic table. You guys do need to show your work, so please make sure you show the step. Some of you just magically go from one step to the other, which is beautiful, but it is being able to show other people. So if you were working with a partner and they said, how did you do that? That gives us, what, 0.00667 moles. We're not at equivalence. So we want to figure out our NaOH. Now, a question that somebody had asked me is the NaOH always going to be the limiting reactant? It depends where we are in the titration. So we're going to do the math and figure out where we're at. So 0.180 molar, and our volume we get, and it is our limiting reactant. So you could actually answer, I often ask that question, where are we in the titration? Well, if our strong is still limiting us, going back to my titration curve, we're here. This point, the equivalence point, what is equal at the equivalence point?
The moles are equal to each other?
The moles of what?
The reactants.
Yeah, so the moles of the reactants are equal. That's why it's called equivalence. But we're not there yet because our moles are not equal. Right, so it's limiting reactant. We subtract the smaller number, which is still the NaOH. If the NaOH was the larger number, it would mean you're post-equivalence. You're at the point of excess. All right, subtracting. This guy will cancel. We'll add to this side. And see how I do in my head. 4, 8, 7. And again, I like to label acid base. We plug into Ka, we solve for your X. So I'm not going to go through all the steps. Your X's are going to be your hydronium. There is a question that comes up often with this. And I'll give you guys a moment to plug in and see, to punch it in. I'm pretty dang positive my answer is right, because I've used these notes. Right. So you get your X and you take your, you would tell me your value of X. I think my answer is wrong. You guys punching it in? I'm trying to find my old notes. I think I took a question out and I moved my answers the wrong way. Because I got 7.02. So my base would be on top, right? My acid would be on the bottom. So, oh, I should pause my talking. Right. So I got like 9.5 times 10 to negative 8 for my x. And when I log it, I got 7.02. Well, of course, if I do it correctly. Did somebody else finish it? Find my mistake. Did you get 7.02?
I got the same answer.
7.02? All right, so let's change the one up here. So this one should be 7.02, and we'll figure out what that one is.
I have a question on that, Dr. Sherpa.
Go
ahead. Do we have to change back to molarity?
No, because it's the answer that you asked me. If you're in doubt, though, Megan, you always can, but because we're not at the equivalence point yet, since it's a ratio still, you don't have to go. You don't have to go to molarity. But again, if you're ever in doubt, just go to molarity, and you'll notice, oh, I'm dividing by the same volume. It doesn't matter. When you have to is if it's an x squared problem. Or if you're plugging straight into the negative log, that has to be molarity. All right, so our answer is 7.02. The other point I wanted to make on this one is we've already passed neutral. We've just barely passed neutral, even though we're not at the equivalence point. We're actually nowhere near the equivalence point. This is taking this like a real step further, like for the A+++ student. It has to do with the Ka value. This is a fairly weak acid, 10 to the negative 8th, which means our pH started already, when it's in the buffering range, when we're in this range, it's gonna be around the pH of the exponent, which means 7 to 9. So in this range, it's already, this whole curve is like shifted up. Often how they'll show that, I do have a red, is you're gonna start at a low pH and it actually initially goes up and then it makes this other jump when we get to the equivalence. And that's because the Ka value is already so small. It's telling us our pH when we're in that range is gonna start changing pretty much. Yeah, all right. Some people notice that and some people don't. So we're gonna do the equivalence. I recommend, it's still the same problem, I recommend writing your mice chart. What I have found is, because people are like, oh, I won't have enough time. You can actually leave the H2O off because it's not gonna matter. Some people like it on, some people are like, it doesn't matter and they leave it off. What I found is the students who actually go through, I don't know if I know how to admit somebody. The students who actually go through writing the chart actually get done faster because they can see all their numbers clearly written out. And once you get used to the chart, it's a really nice systematic way of walking through this. And when it's a continuation problem, it's actually a pretty simple problem to do. Because we already know the initial moles of the Haeckel. So we don't have to go through that step again. So that is my moles. From up there, it keeps carrying through. The NaOH is what we're adding, and it's going to keep changing. At the equivalence, the key at the equivalence is these are the same. So which is the limiting reactant? Well, they both are. You've hit that perfect point of bliss. It's exactly the right amount. And so they cross out. Some people like to make their full chart and show the subtraction, but you can just cross them out at that point and move them over. This is the conjugate base. So a couple things are going to happen, and this goes back to the question you just asked, Megan. One thing that happens is all you have left now is one species. So it's an X squared problem. The other thing is the acid is gone now. We have a base. You can no longer use Ka. So at the equivalence is the flip-flop. You switch. Whatever kind of K you were using, you switch. So if we were using a Ka, we're going to switch to Kb. If you were using Kb, you would switch to Ka. So you can just state the formula 10 to the negative 14 divided by your Ka. That is your Kb. And I recommend you're going to write to not lose that dreaded point of show your formula. You're going to write out your little piece. Now, this is a question that Erin has asked me a couple times. And every year there's usually several people. It has to do with the equation that we wrote is not the equilibrium equation. It is the equation for the mice chart to tell us the number. We now have flipped our whole perspective. At the equivalence, the whole thing flips. So initially we were calling this the acid and this the conjugate base. At equivalence, we now view the whole thing through the eyes of the base. The conjugate base is what we're viewing this from. It's the only thing that was there. And so now it gets to be called the base. It's no longer called the conjugate. What happens, I don't write the second equilibrium, but what happens, I will write it on here just for your information, is this NaOCl in the water actually goes through an equilibrium where it goes back to some of the Hochul and some of the NaOH. A very small amounts. If you remember that percent ionization problems, they're usually less than 1%. All right, it is X squared over the base. So back to the question you had just asked me, Megan. You have to have molarity here because there is no ratio. X squared, you always have to have molarity. So we need the total volume. And this is the piece why I wanted to do this today and record it. We have to find the total volume. It was not given in this problem. We know that the Hochul is 50 mils, and that's from up here that it told us. We had 50 mils, that's the same 50 mils. But how much of the NaOH do we have? Well, we know the moles of NaOH at the equivalence. And we also know the molarity of the NaOH from up here in the first part of the problem. And my pen's running out. So if you take the moles divided by the molarity, and again, that was the molarity from up there. So when you flip the molarity on its head, it becomes 1 liter over 0.18 moles. The number in front of molarity stays with the moles, and it moves to the denominator. For those of you who are good with factory label, so if you had Bernadette or myself, you're probably pretty good with this. So we would just take that and divide, and I'm not trusting any of my numbers I wrote down now. I got 0.037. That's going to be liters. Somebody should, yeah. So the total volume is, we have to add the 50 milliliters and that, so it's going to be 0.087-ish liters, right? Change your 50 mils to liters. And we're going to actually go through this, or you guys can, to give you an answer. Right, when you get to X, it's Kb. So if you have it nicely lined up, your X is your hydroxide. When you're working with Kbs, you're dealing with hydroxide. I got 1.48 e to negative 4. And I wanted to make a quick comment to all of you because several of you were here last night or today and you were reading your numbers to me and I'm like, yeah, that's good. And people were like, how do you know when it's close enough? I'm looking at the exponent. And so if you got 1.46, this last digit is different. We're in the same ballpark. And that our exponent is the same. Now remember, when you take the log of that, that is not the pH. That's the POH, so you'll have that extra step. So I got 10.17 as my answer. And I would ask, does it make sense? I'm going with it. I think it makes sense. The reason is the conjugate base determines the pH. What we call the conjugate base determines the pH. It was that question on the previous exam that said, does your answer make sense? And it was the salt question. It was the one with the hot dog. And it started you with an acid, and then I suddenly switched you to the conjugate base. And that's what equivalence does. You're starting with something. In this case, we're starting with the acid, and we're switching to the conjugate base. It takes practice. It looks pretty easy when your teacher's doing it, or easy when you're walking through the homework and you have the answer key there. But that's why the lab that I will be posting later today for Monday just walks you through more practice. All right, so since it's a base, the pH should be above 7. So to give a full answer, you would just say conjugate base determines pH, and so base above 7. I've run out of room. Questions before we fill in the boxes? All right, so we're gonna go for the boxes. Some of these are easy. Like one of the boxes, actually all the answers are in part B. We've got every piece of it. So here we go. It's your bonus point chance before we're done. You guys are all here for that. Somebody go ahead, give me an answer. Give me one of the boxes. You can pick any box you want. Everybody's hesitating. I'll do the easy box then. Oh, look at that. Up here, it says X equals the hydroxide. That is the number that goes in the hydroxide box. Look how easy that was. So 1.48 e to the negative 4, and it is molarity. So I'm pretty sure you all know how to find hydronium. You can change your hydroxide to hydronium, or you can change your pH to hydronium. I like to do 10 to negative pH. So whatever that is. Oops. Oh, of course.
I think it's oh, never mind.
Oh no, I pushed the wrong button on my calculator. It was one of those moments that was giving me a syntax error, and I'm like, really? Well, I'm being recorded? I made a mistake? Yeah. Right.
I got 7.14 E11.
So, yeah, we're in a similar ballpark.
It's okay.
All right. So, up here, remember it was X squared? 2 of the boxes have to be X because 2 things were X. So the hydroxide was X, the hydronium's complementing it. Now sometimes the X will be the hydronium, it's however you labeled it here. So something else has to be X. This was my X value from up above. And if we go here, the X is the conjugate acid. So that's this guy. This is my conjugate acid. And again, it's back to the conversation I've been having. I'm pretty sure it's been with Aaron and also Alexander that at equivalence, we switch our perspective. So the conjugate base now becomes the base, and what we were calling the acid now becomes the conjugate acid. I don't recommend that you write the second equilibrium equation out, but you can if that helps you initially. For most students, then there's just too many things there in front of them. All right, so we would just have to punch this number in and see what we get. And oh, I'm sorry. I'm taking a step ahead. That would be our 1.48 e to negative 4. I was on to the next question. So this is X. My conjugate acid and my hydroxide are X. All right, so the OCl, that's this guy. This is going to come down here. The 0.0067, whatever that, I just punched it in, 0.0767 molar. And hopefully my numbers are all good. But you can see I don't lose sleep over if I make a simple mistake. I try my best. All right, so what about the sodium? I keep telling you guys you can cross the sodium out if you want. Well, the sodium partners with the alkyl up there. So even though the sodium's just floating around doing nothing, it's there. It's still there. So these two are partners, and so they are the same. They went together. This is a tough question. It shows up on the homework. I put it on here to walk through it. It's going to show up on the lab. So hopefully, after you do it a couple times, you'll start being able to fill it in. Again, all the numbers are up there. It's just saying, looking at it in a new way, can we see how to fill it in? So questions. Did anybody walk through my math, or we're all happy with it, hopefully? Yeah. A reminder, when you give pHs, please give pHs to 2 decimal places. And all the other numbers, you can give 3 sig figs, and that should work. And then I sent an email out today, and I'll send another one Sunday with what's going on next week. But today, your study set and worksheet are due. Yeah. And start on your famous chemist thing. And I also asked, start thinking about what you might want to do for your demo. So if any of you here have a question on this, otherwise I'm going to stop recording and I can answer other questions. But unless somebody sees a glaring mistake that I should make for everyone. All right, I'm going to stop.